I would also like to welcome you all. It's great to have so many people joining this open master class today in engineering subject. So my name is Fumiya Iida. I'm wearing two hats. On one hand, I have my academics in the Department of Engineering, but also I'm an engineering fellow at the Corpus Christi College. And I would like to share with you a bit of my way of looking at the world while I'm being in Cambridge for last years, and I'd like to give you a bit of flavor about how you feel like when you're studying in Cambridge, and try to give you some flavor of the teaching activities in the engineering department. So let me start with some basic introduction of Cambridge. So I think many of you have already know all this information, but I just want to give you what, from my point of view, what's the really advantage being in Cambridge, right? So I have been in Cambridge for many years, but one of the most exciting things in Cambridge that we have so many opportunities to meet lots of people with different background. First of all, it's very close to London. So London, we see a lot of intellectual activities where we can actually go quite easily. But also the Cambridge itself has a really long history and the depth and breadth of people in this small town. So, first of all, the Cambridge has more than 800 years of history and the great minds around in the city. So we have 110 Nobel Prize laureates. But in addition to that, we have a lot of notable alumni in Cambridge. Starting from Isaac Newton, Charles Darwin, all the way down to Alan Turing, also Ashby. They are quite famous in engineering and mathematics and physics. Paul Dirac, James Maxwell, biology. Francis Crick and Andrew Huxley, and so on and so forth. So this is a really place where I see the most exciting aspect of Cambridge, that we're surrounded by history and surrounded by current academics that we can actually inspire me in research and teaching. So I myself is a robotics engineer in Cambridge, doing research and teaching in the subject of robotics. But my viewpoint while living in Cambridge is really looking at what is the way how we should study robotics, given all this historical background and the diverse people surrounding ourselves. So I just want to give you a bit of idea how I look at the robotics at the moment and give you the flavor of a study of robotics in Cambridge. So I just want to give you a very interesting video here. So this is probably one of the most inspiring video in my career as a scientist. So when I was a student, I was working on robotic subjects, but I encountered this video when I was studying leg locomotion of robots. So this video is kind of showing the famous dog in the leg locomotion community. It's called Faith. This is the name of this bipedal dog. So this dog was famous because it was born without front legs. But somehow this dog was managed to survive, just only with the hind legs. She can do all sorts of necessary processes like walking, running, standing, sleeping, eating and scratching backs and so on and so forth. When I encountered this video when I was students, I was really, really shocked because, as a robotics engineer, we'll probably never ever build machines like this dog, right? So originally designed as a four-leg animal, so four-leg robots. Chopping off two of the legs, how we can make robot surviving very different from original design of it. So and when I saw this video, I think we just need to rethink about how we should think about designing and building of our robots, and that's the kind of starting point of our my career and the robotics bio-inspired robotics. So I just want to briefly look at why this is actually possible in nature, but why this is not possible in the conventional engineering and especially in robotics. So this is the lecture slide borrowed from John Gardner, is another Nobel Prize laureate in Cambridge. He's a biology professor. That he always shows in his lecture that the most interesting aspects of biology is actually this, right? The scalability of our life from a single cell to a bug of many cells. So every single life of our cells starts from one cell as an egg cell, and then we grow to a bag of 10 to the 10 cells before we're born. And then from there, we still grow about 1,000 times, right? And this process is enormously complex, and that this is something beyond our reach in engineering methods. And this is just the beginning. And if you look at our body, like our body is replacing, 100 million cells every minute. So our body is by no means a static structure, but it's very dynamic. It's replacing cells all the time. And the complexity is not finished here, right? So if you look at the counting the molecules, the number goes a lot larger than this. So in general, I think this is really interesting that how biological systems start with such a small scale, but goes to really large scale after all. And all of these things are kind of directed by a very small amount of information, like a 700 megabyte is believed to be information stored in the genome. And this is all enough to make all these complex systems. So how can we think about such a system in engineering ways? And that's my starting point of robotics, the bio-inspired robotics research. So if we need to think about how to build robots, we really need to think about the scale. So first of all, our human body is incredibly complicated, and if you count, cell by cell, this is the numbers equivalent to 1 million times more parts than Airbus A380 is probably the biggest robots we can build at the moment. And this is not enough, that we just need to also start thinking about how to replacing the cells all the time while we are alive. And also another interesting things that we learn from nature is that the amount of information in human genome. So this is the blueprint of the design of this complex system, but the amount of information in this genome is a lot smaller than we actually think. That it's just do a simple math here. This dividing number of cells by the amount of information in genome. It gives us like 1 bit of information in genome is basically in charge of the design of, on average, like 1,800 cells. So this basically means that the genome is not really telling our body like how our body should be built in an exact way, but it's just only guiding the direction of growth in the building process. So this is really a new way of building robots, because conventionally we have to design robots parts by parts by human designers, but the nature works in a completely different way, and how we can adapt to the natural way of building robots is our one of the biggest challenge in our research at the moment. So one step we just need to think about is, let's start with a really simple model of a new way of building robots. So this is what I call the robot genome model. So instead of building robots by designing parts by hand, we think of some virtual genome, robot genome that stores the information of the design of robots. But this has to be somehow guided by phenotyping process, like a translating information in genome to make a physical robots afterwards. And then thinking about how this physical robots evaluated to influence the next generation of genome. So this is a kind of self-organization process, like how physical robots can be potentially built automatically without, intervention of human designers. And we would like to discuss how this can be possible and how we can achieve this kind of things in reality. We just need to think about both informational processes and physical processes here, right? So that's something we need to think about. And we want to discuss this a little by little, how this kind of robot genome model can be achieved in real world. So the first step of this kind of research can be done in the so-called formation of pattern research. So if you look at our nature, the patterns are everywhere. So we see patterns in the seashells, or patterns on the surface of biological systems, or patterns in the chemical reactions and so on. So how can this kind of global patterns can happen in nature is the kind of starting point of self-organization of robots. And what's really important here to think about is the local interactions, right? So we cannot really represent dot by dot in the surface of this cheetah, but we want to have a small bit of information, piece of information that guide the growing process to the global pattern. So local interaction leading to global patterns and structure. This is the question we need to think about. So how can we do such a study of pattern formation? Actually, this kind of research has a long history, and one of the first pioneers in this field is our British hero, Alan Turing, right? So he's also was a student in Cambridge, and he actually started what he's known as the father of Turing computation. But he did lots of other research, and among others, the chemical basis of morphogenesis is actually one of his a big achievements. So what he is proposing here is a mathematical model of the so-called reaction diffusion model. So in this model, he proposed basically two chemicals that interacting to each other. One of them is called activator, and the other one is inhibitor, right? So this is just a virtual model of chemicals of different kinds. But basically what they do is the activator shows the patterns, but this is also can be inhibited by the other chemicals when they're interacting to each other. So assuming these two types of chemicals and how they interact to each other is determined by an equation here. So I don't want to go into the details of the equations because it's actually very complicated. But very briefly, this equation has two parts. One of them is diffusion and the other one the reaction. So diffusion part basically push the chemicals away from the current location, depending on some rules. And also the reaction part is how these two chemicals interact to each other. And the results of these two terms of this equation actually tells how the chemical actually shows up in each location in the two-dimensional space. So this is a really simple model. Well, equation itself is kind of complicated, but local rules of each location can be represented, representing the global structure in the system. So I can just show you some examples of this chemical reaction here, the reaction diffusion model. So one famous model is a Meinhardt model. So this is one of the simplest models that follows the Turing definition of reaction diffusion. So this actually have a two set of equations. I don't want to look at the details of this, but we just want to see the structure of this. And part of it is the reaction diffusion part, and the other part is the reaction part, right? And the beauty of this is that if you change one parameters of this equation, and then the global structure, global pattern changes significantly. So the kappa A here, when you put 0 here, and then you show this kind of dotted patterns, while if you change this kappa A to positive number, it shows more like a stripe patterns. So this is a kind of example showing that the simple rule, the local rules representing a global structure in the pattern. So this is a really, really good starting point, how we can think of, genome and the global patterns relationship in this relatively simple, reproducible mathematical equations. And then this is a similar model. Again, we have a reaction part, the diffusion part, the reaction part in this equation. And this one is a little bit different structure, but it shows a more dynamic patterns over time. The interesting thing is, again, just by tuning these two parameters, the global structure changes a lot. And that's a really interesting starting point, how patterns can emerge from a local structure. So this is a really good starting point. It's already a long history of this research, but what we want to see is how we can deform these equations into different forms so that we can apply to the robotic systems. The next example I just want to show is the John Conway's Game of Life. So John Conway is, again, another Cambridge mathematician who started, who was inspired from Turing research on the reaction diffusion, but he thought of the mathematically simpler way of defining lifelike behaviors. So in this case, the interaction is defined in a much, much simpler way, that we only think of black and white tiles in two-dimensional fields. So we're just thinking about the patterns of this neighboring tile colors. So if you look at the neighboring the colors of neighboring tiles, you can actually define the local rules as if you have too many too many black tiles around it. It always goes to white. And if you have exactly 3 white tiles in the neighboring cells, and it becomes and black. And if you have less than 2 black tiles, and it becomes 0, regardless of color of the central tiles. So by having this lookup table, this is basically a local rule determining how the color of tile has to change. You can actually see behavior like a Turing reaction diffusion in a much, much simpler way. So just want to give you one example of this kind. So if you have a pattern like this, the black tiles is always black because of the conditions set by neighboring tiles. So this kind of pattern will stay for a longer period of time. But if you have a pattern like this, black, 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 on the horizontal line, it actually switched to the black, black, black in the vertical line, just like this. So you can actually try this kind of, the rule applying to this situation. And then you can actually see alternating pattern from horizontal to vertical and vertical to horizontal. And this actually shows really interesting dynamic patterns by just having a simple rule like this. So there's a research, a lot of research in this area, and the discovery of different patterns in this Conway Game of Life definition. And then you can actually see really interesting lifelike behavior like that. I just want to show you the videos rather than explaining a little further. So, so this video is copied from YouTube. There's many examples of this kind that the Conway's Game of Life has been studied. So here is showing some patterns, dynamic patterns as moving around just by following Game of Life local rules. And we see, even though this is a lot simpler than Turing reaction diffusion model, we see quite lifelike behaviors with lots of diversity of behavior patterns, and that makes things really, really interesting. If you go really, and there are lots of artists, making this kind of movies of patterns and trying to find the new ways of finding a stable repeating patterns, lifelike patterns in this format. So this is a quite interesting starting point, and you can actually, try look for some other interesting patterns in the internet. There are many examples you can find in the internet. So try find it in the internet and try doing it yourself. But what we really want to see in the next step is how we can bring it to the real world, right? So how we can make it a robotic system. So we see a lot of interesting patterns. These patterns are not really like animals or robots so far. So we just want to think about a little longer time scales. We're looking at so far here and now time scale, but we want to bring it to growth process or evolutionary process in a more interesting manner. So one way to do it is a user-computer simulation. So we can apply similar thing like a game of life principle to the computer simulation, so that a computer can come up with many different kind of robots like this. So the patterns can be evolved through lots of trials and errors in the evolutionary process. So here, all these virtual robots are created in computer simulations almost 30 years ago, but they actually made all these robots without the human designers, right? So the virtual evolutionary process can actually make robots like creatures in the virtual environment. And there's so many different kind of interesting virtual robots here. I also recommend you to look at it in the YouTube, like how they actually did it. The trick of this evolution to happen is, of course, inspired from a natural selection process proposed by Charles Darwin, also another Cambridge alumni. And so the idea here is that basically the principle of survival of fittest. So what we need to do is the phenotyping. So we have some information in the local design of the robots, and then put it in the real robot structure and evaluate it in the real world environment. And if the performance of the physical system is good, then the genome information is kept for the next generations for reproduction. And then we can repeat all this process. Then we can do a trial and error optimization process of the robots without really, using human intervention. So the question now is how we can bring it to the real world system. So what we want to see is the robots we saw so far is all the virtual, the computer simulation, but we want to bring it to the real world. So this is one of the main research challenge we have been working on in the last 5-10 years. This sounds like a really complicated challenge, but it's not impossible if we think of some technological advances. So what we are doing is so-called mother robots. The concept of mother robots is a robotic system that can translate the genome information to the physical robots, but also physical robots to be evaluated in the real world so that the genome can be updated over the iterations. So the first challenge is how we can translate the genome into the physical robots, and that's one of the research we have been doing in our group. So one way to achieve is this is the first version of mother robots. This is equipped with end effector, with 3D printing end effector that can create different kind of structures, mechanical structures automatically. So this robot is able to make kind of cup-like structures and a stick-like structure, and put them together by bonding them. And then the robot can actually make scoop in the end effector so that you can do, things like water transportation from one dish to the other. This is a very powerful 3D printing approach. So the robot is able to make a very different kind of mechanical structure at the end effector, like making a big tweezers or small tweezers, or it can make also like a fork-like structures. So this is a really a big step forward, because the robot can actually change its own shape automatically without human designing, a human building mechanism for this robot. And the breakthrough of this research was done actually by material research, actually. So the materials we use for this robot end effector is the so-called hot melt adhesive. So this is a polymer that can change the strength and the adhesiveness by controlling temperature. So the robot can actually actively change the mechanical structure by applying heat and some the motion principles. So this is a really good start to make robots' mechanical structure more dynamic and change it over time. But of course, the next challenge is how we can apply the design process itself, right? So the robot can change the structure, but how the robot can design the next generation is the kind of interesting question. So what we did next is that this is a second version of mother robot that is able to manipulate a variation of objects, and they can put together into different shapes in the child robot. So this arm is a mother robot, and this modules the rods made of modules are child robots. And once child robot is made, can be put in the experimental arena, and then can be tested in the physical world. So, so what this mother robot doing is making all different kind of design of the child robots, and to measure the performance of the child robots. So in this case, the mother robot observing how the child robot is escaping faster, so locomotion distance in a given time. So measuring the distance and try to optimize the mechanical structure for the better performance of locomotion. So having this kind of measurement of locomotion, we can assess which design is good and which design is worse. And then pick up the good designs and pass this design information to the next generations, and then make another 10 set of robots in second generation, and so on and so forth, and repeating 100 generations and 10 generations, building 100 robots. We usually see the performance better compared to the original versions. So just to give you some examples, so this is the evolved robot from all this evolutionary process. So the mother robots usually start with the smaller robots like this. It already moves a little bit, but of course, mother robot can actually make a much larger robots like this. And then the larger robots can move faster, and therefore it's better fitted in evolutionary dynamics. And we can actually see the evolution of physical robots in this way. This is really exciting because humans are not really designing this robot, but the robot is designing robots, and that's the kind of very fast breakthrough we can make to achieve this kind of physical evolutionary robotics starting. But obviously, there are lots of dead bodies behind this evolution. So all of these robots are not performing any locomotion. So these are kind of species die out in the evolutionary process, but this is kind of necessary process in evolution to make a better results in the end. So I hope you have a bit of flavor of how the robotics research is moving more and more towards robotic systems. So I just want to give a bit of brief history of myself. Like I started my robotic research in the 1990s, making a very conventional robots. Like this is a face robot I built in the first time, which took like 1 to 3 years to make one of these robots. So therefore, we can explore only 2 or 3 different types of this robots. And when I started my PhD in 2000, building a one robot becomes about 3 hours. So therefore, we can explore lots of different kind of robots, about 30 to 50 different types during my period of PhD. But now in 2010, one of these robots can build in something like 30 minutes. And the latest version we have, we're able to build in 1 minute. So we can actually try different types of robots to the scale of hundreds to thousands of different robots. So I'm really excited to build many different kind of robots, just like evolutionary dynamics produces in nature. And that's a really exciting part of my research, and I'm working a lot of this kind of things with my students at the moment. So I just want to give you a bit of summary of my lecture today. That the complex system is a really the groundbreaking, the fundamental challenge in engineering, but we have a lot of new technologies such as 3D printing or actuator sensor materials, and lots of engineering efforts put together into making more and more complex robots, and that's why we're able to do things like evolutionary robotics. But we need a new design paradigm. So we cannot really build future machines by hand all the time, but we need some automated self-organization process in the design and fabrication of future machines, and that's what we are interested in. And hopefully at some point in the future we can make this complex systems like ourselves. One of the challenges we did is like trying to make a humanoid, baby humanoid in the 9-month period, just like human development in the early stage of our life. And that's something we are really looking at. So we still don't know how complex we can go eventually, but I think that's a really interesting challenge in the end. So obviously we have lots of collaborators in this research project, and many of them, this research is possible because of my very talented Cambridge students, and I'm hoping that you can join our research project in the future. So if you're interested in more details of my research, please feel free to visit our website or send us emails. And you can also visit our homepage to see more videos of our research projects. And with this, I'd like to stop my presentation, and I'd like to open the floor for the question and the answer session.
Fantastic. Thank you so much. Such an interesting talk. We've got loads of questions coming in already. So I've just kind of realistically, we're not going to get through all the questions, but we'll answer as many as we can in the time we've got, I think. There've been a few admissions style questions that have come in relating to sort of subjects that are being studied at A-level. So I'm actually going to save those for later because we've got an admissions talk later. So I think they'd be more appropriate to answer later. And we're going to focus on the more sort of technical content of your talk for now. So we've got a couple of questions that have come in that are quite similar. So what is a phenotype? What is phenotyping?
Oh, thank you. So the phenotyping is really about the translation of the information from genome to the physical system, like a biological body, like our body, or physical robots in the case of robotics, right? So the genome, it's basically generation to generation in evolutionary process. What is passing is the information rather than physical body, and how the information translated to physical body is an important process in biology. And also in engineering process, how we can build the physical robot is a real challenge, and that's what we call the phenotyping, and that's one of the central question in our robotics, evolutionary robotics research.
Great, thank you very much. Somebody's asked, how did you decide robotics was the strand of engineering that you wanted to go into originally?
Yes, that's a very good question. I had a lot of thinking when I was a student. I originally wanted to do aerospace, aircraft, rocket science, and so on, as a mechanical engineer as basic training. But then I was more and more interested in integration of the parts. Rather than looking at parts, I want to see the integrated systems. And if you go to rocket industry or aerospace industry, what you can work on as a single engineer is a very small part of the big thing. And you can actually very rarely see how the whole thing's put together and working. So, so that's why I moved into robotics, because robotics is about integration of parts. And really fascinating thing is, integration. Usually, if you put parts together, things are really, really difficult to make. 1 + 1 is not equals 2. Usually, less than 2. But if you look at biological systems, 1 + 1 is not just 2, but it's sometimes 3, sometimes 10, sometimes 100. And that's the kind of really exciting thing about self-organization and integration science, which is actually the sense of robotics. And that's why I was really excited doing robotics after all.
Thank you. That's really interesting to hear about. Somebody's asked how much biological knowledge is required for biological robotics.
Yes, so obviously what's really important is having your native skills, right? So in my case, the backbone skills and mechanical engineering, and I didn't know anything about biology at that time, apart from the really, really basic things. But as you progress your study, especially in Cambridge engineering, in the third year, fourth year, we will have more and more module choices, like you can learn about biology, like how to do, the neuroscience, the biomechanics, and the biomimetics, and so on and so forth. So it's good to have some engineering, backbone native skills to begin with, and then gradually move into the other interdisciplinary areas. Engineering is really good sometimes because it's more easier to learn engineering earlier at your age and the biology later, because lots of engineering skills you need really systematic learning. Otherwise, it's very difficult to go deeper. So I was really lucky that we start with engineering and learning biology later, so that we can do this kind of field. Quite often, biologists struggle to do the robotics research afterwards. So I think that's one of the advice I can give.
Thank you. Somebody's asked, if the limit of this system is how well the mother robot can assess then reproduce new robots, would it be possible for a mother robot to create new versions of itself in order to overcome that?
Yeah, that's a very good question and exciting question. Well, the answer is no. Obviously, our ultimate goal is how mother robot can replicate itself, and that's what the biological reproduction is, right? But at the moment, it's not possible because we can, the mother robots are a lot more complex than child robots. So, but obviously that's our goal in the future.
Thank you. Somebody's asked, what's currently the most complex robot produced through this method?
Yeah, so at the moment we have a limit of the 5 different modules to be put together because that's the capability of a mother robot. So the robots cannot build anything more than a child robot consisting of 5 modules. But hopefully we will find out some different ways of manufacturing child robots, and so that they can make go beyond the complexity limits at the moment. But that's where we are at the moment.
Thank you. We've had a few questions about AI, so just pick one out. Do you use AI technologies in robotics development, or if not, why not?
Absolutely. So AI is, really exciting technological tools that are available for all of the engineers now, right? So no matter what engineering you do, it's difficult to avoid using AI because it's such a powerful tool, and it's becoming a really commodity for many different engineers. So we all study AI now, and we always make use of AI, but at the same time, AI has its own limitation. So what AI cannot do is really the physical processes. Like they can do information processes in a very, very sophisticated way, but as soon as you put them in the real world, they struggle. So what we are doing in evolutionary robotics is how we can extend AI in a more sophisticated way in the real physical world. And in that way, we are working together with AI researchers how we can make next generations of AI more fit to the real world physical environment.
Thank you. A few people have been asking about the end goal of your research, the end goal of the project. So somebody's asked in particular, what's the end goal in making something like a baby robot?
Yes. So one aspect of our robotics research is really trying to understand, ourselves, right? So what makes us different from robots or other machines, and why machines cannot work like ourselves. So we have lots of interesting real world challenges. Like we work with manufacturing or agriculture or other consumer applications that we want to automate many things, right? There's so many workers in the agriculture field that they struggle with, really difficult working conditions. These are the kind of things that the humans should not be doing, but still robots cannot really replace this kind of human workers. So, the answer to this question is really the robots are not really capable of replacing humans, because humans are doing really a lot better than the current what robots can do today. So what we're really trying to do is, the fundamental difference between animals and machines, and we want to understand how nature works, as well as how we can improve our machines inspired from knowledge in nature. So that's the ultimate goal of our research.
Thank you. The next question, what are the ethical issues you anticipate with these technologies, and why are physically self-evolving robots more valuable than using simulations to analyze different designs of a robot?
Yes, that's a very, very important question that we always need to aware of. With the technology of AI, or with the technology of evolutionary robotics, our robots are getting more and more out of our hands, and that's a fact. And therefore, we need to really, be prepared for how to deal with such a system and how we can, ethically perform the research projects. So, but having said that, the ethics cannot stop this kind of research project, and the AI is necessary technologies now. We cannot avoid AI. We cannot avoid robotics to automate many different kind of things. So we need to really think about ethically how we deal with this kind of technologies, and how we can make our society safe and ethical. In addition to make it, more beneficial and more profitable. So that's absolutely very important, a question that all of us need to think about.
Thank you. Somebody's asked, why did you decide to do a PhD rather than going into industry, which I know is quite an important question with engineering in terms of academia versus industry?
Yes, absolutely. Well, to be honest, I was exploring both ways when I was a student. I tried to get a job in a company or went to a PhD. But I discovered that if you go to PhD, you can also earn money. So it's actually good to study by having some stipend and exploring what you're really interested in. So after all, getting paid is of course important for survival, but what makes our life more interesting and exciting is how you can explore and follow your curiosity and your enthusiasm. So I think that's the kind of balance you need to make. And in my case, I was lucky enough that we had the opportunity to follow my PhD course, and And many of my PhD students actually do the similar choices. So in the end, how you define your happiness and your excitement for your life, and I think that's the critical for your decision in the end.
Thank you. A few people have been asking about how your work might sort of relate to climate change and tackling climate change. So I'm just going to pick one out. Do you think that robotics or AI could play a key role in tackling climate change, and if so, how?
Absolutely. So, the climate change is one of the many challenges we have today, right? So we have a food crisis, we have a water shortage, and we have urbanization, and how to reduce the wastage and so on. So there are lots and lots of challenges in our society. But all of the solutions, all of this crisis, I think robotics and automation is the key technologies to make impact, because in the end, what we are doing as a human, physical activities is the cause of all the problems at the moment. So how we can optimize all the processes, business or otherwise, by using technologies is the missions that all of our engineers, including roboticists, should work on. So in that sense, I'm sure we can make an impact for this crisis.
Fantastic, thank you. Aware of the time, I'm just going to ask a couple more questions, if that's okay. So somebody's asked, is there possibility for the developed robots to become so advanced to the extent where they begin to develop other mother robots?
I think so, yes. In the future, I think that's going to be the direction we're going. We're still far away. I don't know when this is going to be possible. Maybe 20 years, maybe 30 years, maybe 100 years. But I think that's going to be the direction we're going in anyway.
Thank you. And then last questions, just so that everybody gets a little bit of a break before we move into our student section. A lot of people have been asking, how can they get involved in robotics? What should they be doing now in order to sort of develop the knowledge and skills base that they might need if they were to want to follow this path?
Yes, so as I said earlier, robotics is really the science of integration. So you need a really broad set of knowledge. It's, you can start anywhere. You can start from mechanical engineering, electrical engineering, or computer science, or you can start with math, right? I show you all different aspects of engineering, and math and physics are involved in robotics. So you can start with any of these things. But the important thing is that you try to master as many different fields as possible, so that you can have a broader view of the different aspects, so that you can do integration of those knowledge into systems. So yeah, I think that's the advice we can give here.